Okay, we're going to be looking at our next chapter, which you might be surprised to know is another method used to find volumes. It's called the shell method. And let's show you what the problem is. In the shell method, we're only going to, well, let's just show you. I think that's the best way to do it. I want you to imagine that we have a function. Too early in the morning for morning good. Let's try that again. Now that function's fine, but it's not fine for the example I want to give. Here's a better one. Suppose we have a function y equals f of x, you know, something like 4x minus x or whatever it is, right? That kind of thing, right? And you want to rotate this shape about the y-axis. If you try and rotate that shape, right, the shape here, and I should indicate from, let's say, A to B, although it doesn't need to be on the x-axis, I've chosen it to be. Right, from A to B. If I try to rotate that shape about the y-axis, it can't be done using the disk method. And you might say, yeah, we've done rotate things about the y-axis using the disk method. Why can't we do that one? Well, if I was going to rotate this shape, y equals f of x, wouldn't I have to have a y value to start, a y value to finish, and much more importantly, shouldn't this function that's written this way be converted into a function that looks more like that? Agreed? If you rotate about the y-axis, it has to be, you know, x equals y cubed or something. Well, suppose that y was x squared, actually minus x squared plus 4x minus 3. Suppose it was something like that. Do you realize that you cannot really change this function into x equals? Would you agree? Algebraically, that ain't going to happen. So it's a kind of niche market. You know, it's not the kind of thing that you're going to need to worry about as often as the disk method, but it is a problem. How do you rotate shapes about the y-axis where the function is given in the form of y equals f of x, and there's no algebraic way of turning it into x equals? Right. So think of that as the situation you're going to use this new method. But wouldn't it be nice if there was a formula that allowed us to do that? And of course there is one. So I'm going to redraw my guy again at the top. So we're going to look at how do you rotate a function from x equals a to x equals b. That's this guy here. And we're going to look at what it looks like when you rotate it about the y-axis. And here's the formula. V equals the integral from a to b 2 pi x f of x dx. Now you notice how different it is from the pi f of x squared formula. Secondly, we are rotating this shape about the y-axis. Do you notice that the formula contains nothing but x's? So there's quite a difference, isn't there, between this formula and the disk method formula. In the disk method formula, if you rotated something about the y-axis, all this information would be in terms of y's. But in the shell method, when you rotate something about the y-axis, all the information is in terms of x. So quite different methods. Proving that one is a lot harder, so I'm not going to, it would take too long anyway, but there are some quite good animation videos online if you want to actually see where this formula comes from. But it's kind of nice that someone went to the trouble and found it for us. So let's do our first example then. Yeah, question 1 will do. Suppose you wanted to take the function y equals 5 cos x squared, and you wanted to rotate it about the y-axis. So your first step would be to sketch it, and Desmos would do a good job, but since I've got the picture in front of me, I'm just going to draw it. It looks something like that. So that's the shape, and it's going to be rotated about the y-axis. So step 1 is draw the thing, so you get an idea of what region is being rotated about the y-axis. It ends up being this guy here. Step 2. Typically using the information that's given here, write down the formula. So the formula in this case is going to be the integral from a to b, 2 pi x f of x dx. Right. Are you happy? But a would be 0 and b would be this weird square root thing. So it's going to be the integral from 0 to the square root pi over 2, 2 pi x followed by the function f of x dx. Are we okay so far? You happy about where all these numbers are coming from? Right. I want to do a smaller side issue. If you took this guy and you plugged it into Desmos, you would see this picture. Basically, you know, the y-axis is going to be the end of the line on this side, and the x-axis is going to be the end of the line on that side. So we just assume that that is given. This number here probably will not be the square root of pi over 2. This number will be some ugly decimal. But we don't like ugly rounded off decimals. We like exact values. So you may have to do a little side issue. I want to find out when that guy, right, this curve, crosses the x-axis. So I'm going to have to solve an equation. Don't I have to solve the equation when is this guy equal to 0? Now you divide both sides by 5. I'm looking for when is that guy 0? And then don't you just use your knowledge of inverse cosines? And does anybody know that says inverse, by the way, what the inverse cosine of 0 is? What angle has a cosine of 0? What angle?
Pi over 2.
Pi over 2. Can you see where this is going? There, have I now convinced you where that ugly square root of pi upon 2 came from that you won't be able to get from Desmos? Now, Desmos is great if the answer's a half or 2 or 3 or whatever, right? It's fine when you're talking about those numbers. But can you imagine that sometimes you just have to do a bit of algebra to get the exact value? Hopefully not very often, but you know, the few times that it's going to happen, at least, can you see this would be our way of tackling it? So let's return now back to this question. We're finished in basically step 3 now. And step 3 is going to be evaluate this darn thing. And I just thought of something here. Are you okay with me taking the 5 and the 2 and calling it 10? Oops, putting it there. Right. Just thought of something else. Before I start figuring out what to do with this guy, I try and make my life as easy as possible. So in this particular case, are you okay with the fact that I can just pull out the 10 pi outside the integral, get them out of the way, just to, you know, make the job a bit easier to deal with? Okay, this integral is doable, if there is such a word as doable. What technique will I use to find the integral of x cosine of x squared?
U substitution.
Correct. And who is the u sub going to be?
X squared.
Are you all comfortable with x squared being the u sub? Why that was chosen? Right. Cosine the ugly guy. The ugly guy is your thing. So differentiate with respect to x, crossover, and isolate. So what do we have here? Well, we have 10 pi, the integral of an x, a cosine of u, instead of a dx, a 1 over 2x, followed by a du. The x's will cancel. That 2 will cancel part of that 10. Are we okay with that line? Are you comfortable where all the pieces fit to get you that? Why the 10 pi is now only 5 and that the x's have left the building. Now what we're going to do is find the antiderivative of a cosine. Okay, go for it. Antiderivative of cosine u.
Sine.
Correct. And then return back to the x's. Let's see what we get. Right, we're going to get the sine of this thing squared, which is just pi over 2. Take away the sine of this guy. And something really remarkable happened. This x being the square root of pi upon 2 really didn't cause a problem, right? Came out quite nice numbers. And isn't the sine of 0, 0, and the sine of pi upon 2, 1? So you get 5 pi, 1 take away 0, 5 pi. If you rotated this shape about the y-axis, it would look something like this. I don't know if these lines here help or not. Probably not. Wouldn't it look like the top half of some distorted sphere? And the volume of that shape would be 5 pi. So can you imagine the shape being rotated like this? Are you okay with this? Does this have a kind of step 1, 2, 3? It's different. You know, the formula at least is different. But apart from that, it's got a nice flow to it. Any questions about that one before we move on to another example? Did you notice that U subs came into play? Don't be surprised if you see U subs again. Let's make the question a little bit easier. In this one, we are only going to set up the integral. We're not actually going to do it. Oops, scrub that. I'm reading the wrong question. Here we go. We're going to set it up. Right, so let's do that first. If you put this guy into Desmos, you get that fella. If you do x equals 1, it's here. If you do x equals 4, it's here. And if you do y equals 0, it's here. Are you comfortable about that's the shape that is to be rotated about the y-axis? Now I'm going to just set this guy up. Okay, so it's the integral from a to b, 2 pi x, f of x, dx. Okay, 1 to 4, 2 pi x times x cubed dx. I could finish there. I'll take a little bit further. How about pull out the 2 pi and there you go. You comfortable with that one? Got this fella. Y equals 0, x equals 1, x equals 5. I think I'll go all the way to the end of this one. Right, so if you do 1 over x, it looks something like that. If you do x equals 1, it's about here. Let's say x equals 5 is here. Y equals 0 is essentially that piece. There we go. Comfortable with that? You could do it in Desmos if you're not, but I think it's pretty obvious. Let's do step 2. Integral from 1 to 5. 2 pi x 1 over x dx. Oh, would you look at that? Oh, something really cool has just happened.
The x's cancelled out.
He did, didn't they? You weren't expecting that. I certainly wasn't until I saw it. Okay, we got that guy. I guess sometimes the simplest integrals can throw your brain. What's the antiderivative of 2 pi?
Two pi x.
Yeah. Okay, plug in 5, plug in 2. 2 pi times 5, take away 2 pi times 1. 10 take away 2, 8 pi. And that's step 3. It's the end of it. Right, so far, all we have done is rotate a single curve y equals f of x about the y-axis. Do you agree? It looks pretty straightforward. It's quite a plug and jug kind of process. So let's up the ante now and look at still the y-axis, right? So we're still going to rotate about the y-axis. But what do you think I'm going to do instead of one curve? Any takers?
2 curves.
Yeah, 2 curves. So let's have a y equals f of x. And green one. Y equals g of x. Let's start at some guy called A. Let's finish at some guy called B. So the fellow that we're interested in is essentially the area between 2 curves rotated about the y-axis. So you'll end up with one of those funny napkin ring things. Now, I'll show you this formula here and see if we can figure out what the answer for the volume would be. Right, the integral from A to B, that's pretty straightforward. What do you think is going to change from here to do this?
You subtract by that, but with g of x.
Okay. So I heard subtract, which I like. Who goes first? Who goes second?
F of x would go first, then the g of x would go second.
Would you agree that's kind of consistent with all the other situations when you do curves?
Yeah.
High guy goes first, low guy goes second. Is it not that? Isn't that how you find the area between 2 curves? Right. So isn't that basically the area, and that's how far away from the axis of rotation, if you're interested where these will come from? That's it. So there are only 2 formulas. Single curve rotated about the y, area between 2 curves rotated about the y. I think if you can remember this one, you probably should be able to guess that one, right? So let's find a question that's got 2. They're harder to come by, but there are some. So question 7, or at least one like it. It's y equals 10x take away x squared, and it's y equals x, and it's being rotated about the y-axis. To save time, I'm just going to draw the thing. It's almost dangerous, but I'll do it. And you can imagine you could put it into Desmos if you weren't sure. 10x minus x squared is a quadratic that looks something like that. And where are we? Y equals x is just a straight line that looks something like that. You agree? Now, if I had Desmos here, I would be able to tell you that guy. Would you agree this guy's pretty obviously 0, but I should be able to find that guy, right? How would I find it if I wanted to do it algebraically? Honestly, I would just do it in Desmos because it's less work. But if I wanted to do it algebraically, how would I do it? How would I find out where these two curves intersect?
Set them equal to each other.
Yeah, and if you do that, can you trust me that this is 9? Or you can imagine looking at Desmos and finding out it's 9. Will that do? You can prove it yourself later if you feel the need. Okay, so we got everything that we require. So it's a matter of taking this and using this formula. So the volume is going to be the integral from 0 to 9. I'll take out the 2 pi, put in the x, and f of x is going to be 10 take away x squared, and g of x is just going to be y equals x dx, and that's going to be 2 pi, the integral from 0 to 9 of 10 take away x squared take away x. How would I tackle integrating this? What would I do next?
Distribute the x.
Okay. And at this stage, I'm going to do my dot, dot, dot. Would you agree it's just an ugly power rule, and eventually you'd get some ridiculously 17,300 over 245 pi, which you probably notice some of those ugly questions in your test. You don't expect answers to be 2 pi. I kind of love it when it happens, but aren't most answers some ridiculously ugly fraction of pi? Because that's what you get, right? It's just, that's what it is. We cool with that? Area between two curves rotated about the y-axis is just a matter of adapting our formula just a little bit. So how about this one? xy equals 6, x equals 0. Oh, scrub that. I'm on a different situation. I'm trying to find one more of the ones between. I got any more betweens? Oh, that's disappointing. Okay. There might be another one that's between, but evidently it's there's only one question. So we have finished what you need to know if you want to rotate a shape about the y-axis. So what's going to happen next is we're going to look at what do you do if you want to rotate a shape about the x-axis now. Let's show you what that would look like. So let's suppose I have a shape and I want to rotate it about the x-axis. What shall I call it? There we go. And this shape in here is called x equals f of y. And I wish I hadn't made that the origin, so I'm just pretending that's C and that's D. So this is the shape that is going to be rotated about the x-axis. And the formula for its volume is the integral from C to D, 2 pi y, f of y, dy. Is that a shock or not? Would you agree just all the x's became y's? So that's about it, really, isn't it? Just all the x's become y's. So your formula is going to be x equals y cubed, right? And it's going to be from y equals 3 to y equals 5. And you're going to rotate it about the x-axis, right? It's going to be that kind of question. And you're just going to do the same kind of step 1, 2, 3 as we did a little while ago. So let me find one of those guys. So this is question 10. And the function is that guy. There's an x equals 0, a y equals 6, and a y equals 8. Now, x, y equals 6. Oh, I should write down the axis of rotation. We know that we're going to rotate this curve, this guy here, about the x-axis. It's important that you're aware of the axis of rotation, because that does make a difference in how you're going to interpret this thing, right? So we are going to be looking at x, y equals 6. Should I write this or rewrite this as x equals 6 over y, or y equals 6 over x? Because there's two choices here, isn't there, the way that the information is written? But only one of them is valid for this situation. So how do I write x, y equals 6?
X equals 6 over y.
Agreed. Why did you pick that version?
Because you need to have it as f of y for the formula to work instead
Right.
of f of x.
Yep, that's the reason. I was just making sure I drew this picture reasonably accurately. I've tried to twist it in my brain, that's what I was thinking. So this guy is what x equals 6 over y. But isn't that what Desmos is for if you're not 100% sure? And so we're going to start at 6, which I'm going to pretend is here. And we're going to finish at 8. And x equals 0 is doing that. So can you see that's basically the shape? Now, everything that we need is here. The volume is going to be the integral from c to d of 2 pi y f of y dy. So in this case, it's going to be the integral from 6 to 8, 2 pi y times 6 over y dy. And I am getting some deja vu here. Like I've seen this before. Haven't the y's cancelled out again? I can tell you right now, oops, that the answer is going to be 24 pi. Can anybody tell the shortcut that I used to know that that was 24 pi?
The antiderivative is 12 pi y, and you're going a total of like 2 integers for your area.
Right, so basically the difference times 12 pi. Yeah, that's it. So, I mean, not that it's likely you're going to see many of these, but, you know, it's nice to know that you can cut a couple of lines out. If it's a constant that you're integrating, don't you just multiply the constant by the difference in the intervals, right, from start to finish, and that gets you the answer. And that was that guy. Well, let's find a hard one then. Oh, that's a good one. That one sneaked up. Oh, I'm keeping that one because I like it. But I'm not doing it yet. Let's do 13 and then I'll do that one. That should be the last two. 13. I'm pretty sure I know the function, so that's not the problem. But I'm not 100% sure on my start and finish numbers, agreed? So I think we need to do Desmos now. So here it goes. Bears with me for a few seconds. Okay, so the formula that we are going to be looking for. Okay, where have you gone? It does all over the place. That's not good. Can you see Desmos? Oh, good. My screens are going black for some reason. X equals negative 3y squared plus 15y take away 18. Now, the guy that they're wanting has an x equals 0, which is basically the x-axis, right? So that's what the x equals 0 was about. So if I zoom in this guy, it's this blob here that we want. Do you see it? If we move there we are. You see at the top here, this little blob. So I'll draw my version of what that looks like. Right, that's Desmos done its job. Let's return to whiteboard. Right. So you set this fella up now. You just do the integral from 2 to 3, 2 pi y, f of y, dy. I know I cut some corners out there, but you're happy where all the pieces are coming from? Right, there's my 2 pi, there's my y, there's my f of y, there's my start value of y and my finish, 2 to 3. Distribute this and then some ugly power rule. So we'll call that one good. So this one, which got my interest. And this is, as I said, the last one for today. Y equals the square of x. If you draw y equals the square of x, it looks like that. Would you agree? If you do x equals 0, it's that vertical line. And if you do y equals 5, it's this horizontal line. So when you put these pieces together, you have that shape. And for our formula, it's the integral from c to d, because this is being rotated about the x-axis as well. like everything else to do. It's going to be 2 pi y f of y dy. So I'm filling in all the pieces. 0 to 5. 2 pi y times, oh, problem. Isn't that written in a form that we don't want? Isn't this written in the form y as a function of x? Like a bit like the early one, Maggie, isn't it? Don't we want this one to be x as a function of y? So algebraically, what does x look like?
X equals y squared.
Agreed. Are you all happy about where that y squared came from? Just because they give you the information in this form doesn't mean you have to use it in this form. Don't you have to use it in whatever form the formula wants it to be in? If the formula wants this to be a function of y, then you have to convert it. Now you put this fella together. Well, you pull out the 2 pi. You've just got y cubed. And so power rule, add 1 to the power, divide by the new power. Um, 5, 5, 25, 625 over 4, which is 625 over 2 pi. Are you not impressed by how quickly I did that? And aren't you even more impressed that it's actually correct? Or you're just not impressed at all? Okay, well, that works too.
That was very smooth.
Thank you. I had to kind of fish for that compliment, but nonetheless, let me show you a little trick. Totally useless, but it's kind of cool. If you want to multiply, or not multiply, if you want to square a number that ends in a 5, there's a trick. You want to see it? Okay. If you want to do 35 squared, 55 squared, 95 squared, for example. The answer always finishes with 25. You then take the first digit and you multiply it by the next digit. So 3 times 4 gets you 12. 5 times 6 gets you 30. 9 times 10 gets you 90. That's how you square numbers that end in a 5. Cool? Totally useless. Well, maybe not totally, but how many times are you going to do 55 squared, right? Probably not a lot. But it's kind of nice. You can even do it with decimals. If you want to do 3.5 squared, 5.5 squared, or 9.5 squared, the answer ends in a 0.25. And then this digit plus one more, 3 times 4 gets you 12, 5 times 6 gets you 30, and 90 times 10 gets you 90. So if it ends in a 5, decimal or not, and there's adaptations of it that you can kind of do if you want to, you can actually square them pretty easily. So who says you don't learn cool stuff in Calc 2?